So there was kind of a request come in to review just kind of a couple things, basic mathematics and how to translate the way it's written on paper into a machine. That may not be exactly straightforward, and college courses, once you take them, they count as having taken it. So maybe you had a college level math class 20 years ago. Well, that would meet all the prerequisite qualifications to get into a class it was required for. But having it 20 years ago doesn't necessarily mean you remember it. So just doing kind of a quick review here. So we have our basic math operations. I'm going to go through the whole spiel real quick. We went over about forming numbers and how those go together, kind of a review for that, get into the binary stuff. So jumping into our basic operations, so like add, kind of one of the starting points. That just means putting things together, right? 2 plus 2 equals 4, the basic meaning of it. If we have two things, we add two more things, we end up with 4 things. Kind of a basic operation. There's also subtraction, which is the general way we start. You might remember it's just taking away. We could define it that way. But we often want to, jumping up to a more advanced thing, we need all our numbers, right? We need some positive numbers, some negative numbers. Maybe I'll throw that on here. When we list out all the numbers that we have, which goes on forever in both directions, we usually put 0 right in the middle. So we end up with positive numbers going this way. That's kind of our addition one. And negative numbers going this way. -1, -2, -3, and so on. Eventually, the numbers get more and more negative for infinity, which is the opposite, kind of the opposite of a positive number. And that's how we really want to think of subtraction. A technical term, well, I'll put it on here. That's not the letter I meant to write there. Whoops. We want to think of this as add the negative. The technical term for it, from when we break down to mathematically, we're going to call this the additive inverse. Trying to write legibly here. I-N-V-E-R-S-E. So additive inverse. This relates to, well, I'll go with the number 0. Number 0 we're going to call our additive identity. It's an identity. That means it doesn't change anything when we add 0, right? I think most of us are familiar with that. 3 plus 0 is still going to be 3. So it's called an additive identity. So subtraction, we really want to view that instead of the opposite of addition. If we think of addition as increasing things, instead of the opposite thinking of decreasing, we want to think of the additive inverse. Subtraction, or add the negative, or the additive inverse, is the thing we add to a number to get back to the identity. For example, 2 plus something, and we want to get back to the additive identity, which is going to be 0, the number that doesn't do anything when we add. Well, in order to add that, we can add -2. So we want to think of subtraction that way. It minimizes the number of operations we have. We want to, I'm going to list all of them out here. You all probably know what the list is going to show. But we want to minimize it instead of add and subtract being two different things, we want to think of add and add the negative. That way we only have one operation to deal with. And it's going to relate to this additive identity. We want to get back to that whenever we're doing addition. So a very related thing with multiplication, just kind of reviewing all these. I think I have a little bit of room over here. Well, you've probably seen lots of symbols for it in various math classes over the years, but since this is a computer class, we're going to use the asterisk for multiplication. Or I'm a math person, so often in math we just read that as star. So you might hear me say that if you ever hear me just say star for a symbol and talking about the asterisk. So that's going to be our multiplication. Which is like repeated addition. So case in point, this should be familiar from somewhere. So like 2 times 3, well, that really means 2 plus 2 plus 2. We're going to add 2 3 times. Or we could go the other way. Add 3 2 times, 3 plus 3. In either case, we get back to 6. So that's the basic multiplication. Think of it as repeated addition. So we're building all this up from trying to one single operation. That's an important point as we move into computers, the higher level math, where we don't necessarily want to separate everything completely into that long list we learned in elementary school. Right? We want to think of one operation that everything else builds from. So that's going to be addition. Then subtraction is the additive inverse. That's what gets us back to the additive identity. Multiplication is repeated addition. And division, like I'm just going to write a slash for that. That's the one we use in computer programming. That's what this review is leading into. So you probably know the other symbols, divide symbol, fraction bar, all that stuff. I'm just going to use the one we're going to use for computers. And division is the multiplicative inverse. It's just like our additive inverse, our additive identity is the number that doesn't change anything when we add. Well, we also have a multiplicative identity, right? And that's the number that doesn't change anything when we multiply, which is going to be a 1, right? 2 times 1 still equals 2. It doesn't change anything. I should put some arrows up here because this is kind of a disorganized mess. Or the additive identity, 2 plus 0 still equals 2. Those are the things that they don't change anything when we do that operation. So just like the additive inverse, and thinking about subtraction of rather than a separate operation, think of it as add the negative. Division, we want to think of that as multiplicative inverse. And think of that as what would we multiply by to get back to a 1? That always turns out to be a fraction. So like 3 times 1 over 3. Those 3's are going to cancel out, and we get back to a 1. So that's an important way to think about our operations. Slightly different than what you probably heard in elementary school, but our basic operations of addition, subtraction, multiplication, division, and we kind of want to think about them this way, especially in computer programming, as we get into thinking about math and computer programming, because you'll notice all of this is built up from addition. It's one operation, and we defined everything else based off that operation. How much time is on it? Okay, real quick here, last thing, quick thing about this basic thinking is repeating subtraction, negative numbers. The way I like to think about this on the number line, notice how our positive numbers are over here and our negative numbers are over here. Going back to just defining everything with one operation, think about like this. We're defining everything from addition. So just think we try to move to the right, the positive direction, but a negative turns us around. So like this, positive 2 plus negative 2, we start moving in the right 2, but then the negative turns us around and we get right back to where we started. So think about that negative as turning around. And a multiplicative inverse, that's going to be like a scaling factor. So in this quick example, 3 times 1/3 gives us 1. It's like we start at 0 and try to move to the right by 3, but we scaled it. We only want 1/3 of that. So it scales down to 1/3 of the amount we actually moved. And that's just kind of the general idea. We want to try to picture these numbers instead of that counting thing you originally learned, is this build up on our number line. We're always trying to move to the right. Negatives turn us around, we go to the left. And division or multiplicative inverses scale us down. They just squish everything down. In multiplication, we could take that as stretching. That might be a good way to think of it. Multiplication stretches out how far we're moving, right? 2 times 3 means we're going to add 2 3 times. So we're going to add 2, we're like stretching it out 3 times. Division is the opposite of that. So instead of stretching it, we're squishing it down. And we'll always try to move to the right, so negative turns us around. So 2 negative signs turn us around twice. So 3 minus negative 2, we're going to turn around twice. We start trying to move to the left 3, or sorry, to the right 3. Start here, try to move to the right 3, but then the negative sign turns us around. Another negative sign turns us around again. So we still end up going in the positive direction, eventually up to 5 there. But subtract a negative becomes a positive. And same thing with multiplication. Negative 2 times negative 3. Well, we have the same thing here. Ultimately, that's 2 plus 2 plus 2, but that's like negative 2 plus negative 2 plus negative 2. So it's like it's trying to move 6 in the other direction, but another negative sign turns us around again and gets us back in the positive direction. Just a slightly different way to think about the basic numbers. If that was too confusing, I'm going to do a quick recap on basic operation after this. But this is kind of the way we want to think about it, building from a single operation. Everything builds off of addition here. Okay, hopefully that wasn't too confusing there. That's kind of one of the core concepts of modern math. And machines are actually built on modern mathematics, not the traditional mathematics. With modern math, we build from the operation, not the numbers. In elementary school, the reason I did that one first is because you probably remember what you learned in elementary school. And counting is very natural for people. We usually learn to count when we're very young. So in elementary school, when we're first learning math, we build that up from counting. And the reason I didn't do this first is so this would be fresh on your mind, because if you're watching a review video, this is probably the one you're going to remember from elementary school, hopefully, and how all these operations build up and how we get to math. We're just kind of going through the whole process here just to make sure everything makes sense. So we start with counting, right? I'm just going to draw some dots up here. 1 dot, and 2 dots, 3 dots, and so on. Just the basic idea of counting. As we get more things, we have numbers that represent those. Then we get to school and start applying math to those numbers, finding that we can do combinations of counting, basically. So in that first section, the only one I defined this way was addition. But we'll take that same example, 2 plus 2. This means we're going to count multiple times. Like we're counting 2 dots. I'm counting 2 more dots. Then if we just go through 1, 2, 3, 4, we end up with 4 dots. So 2 plus 2 gives us 4. And subtraction is kind of the opposite of that. Instead of adding on, putting more dots in there, we're taking dots away. Typically that symbol, which probably doesn't show up very good on the video, a little dash. I think everybody's familiar with that. So this time I'll do 3 minus 2. Kind of the same thing. So 3, our starting point. Going to put a couple dots there. And here, instead of increasing the number of dots we're looking at, subtraction, we're going to decrease them. So to represent this, I'm going to draw holes for the dots to fall in, right? So as this moves across here, 2 of those dots are going to fall in our holes, and we're only going to be left with 1 dot. All the way back to elementary school, I wasn't sure where to include in a math review, so it's like, well, might as well include it all, just to make sure it's all there. Then we can build up more operations from this. What if we want to add a bunch of times, right? 2 plus 2 plus 2. Adding 2 3 times. This is where we get into multiply. Well, multiplication, it's easier to write. Multiply is a slightly shorter word to write on the board, which this is a computer class, so I'll go ahead and put the asterisks. I'm a math person. We often refer to that as star when we write it in math. So you may hear me say that sometimes. If you hear me say star, that means asterisks. But multiply, how many times are we adding? So we're adding 2 3 times is what that symbol means, right? So putting the dots in here, we're adding 2 3 times. So in total, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We end up with 6 dots. Then division is kind of the opposite of that. Instead of multiple additions, it's repeated subtractions. So that's the symbol we learned back in elementary school, but for programming, we typically use the slash. So that's what I'm going to write here. So let's say 4 divided by 2. Same way multiplication is repeated addition, division is repeated subtractions. So we're going to start, just the counting version, start with 4 dots. And we want to know how many times we can take 2 away before we can't take any more away. So I'll just throw in some holes here. So just 2 holes. Some of the dots are going to fall in. Those first 2 dots are going to fall in those 2 holes. Then we have 2 more holes. It's going to take away the rest of those dots. And then we're left with 0 dots, right? There's not any left at that point. because they're all going to fall in some hole. And we did that 1 time, 2 times. So that means we can subtract, if we start with 4, we can subtract 2 times. That's basically the idea of it. Doesn't always work out evenly, right? 5 divided by 2. So we start with 5 dots here. 2, 3, 4, 5. And how many times can we subtract 2? There's 2 holes. So we'll take care of those 2 dots. 2 more holes, going to take care of those 2 dots. And we only have 1 dot left, so 2 holes is going to be too many. So we're still left with 1 dot. I've just drawn an arrow. And that's the idea of a remainder. And that can be a very powerful concept in math. This is a low-level review, so not quite getting into it, but we can do a lot. Sometimes the remainder is the important part. So that leads into our modulus operator. Sometimes we want how many things are left over. Remain. When we take away 2 times, we can do it 2 times. We have a remainder of 1. And we can work with the remainders. That's very important in computers. You'll see that more and more. But that's the symbol. We use the percent sign typically for the symbol for that. And with counting things, we can kind of continue on here. What if, so we saw what happens when we add multiple times. What happens is, can we multiply multiple times? So like 2 times 2 times 2. If we take 2, we multiply it 3 times. That's our exponents. The first idea of exponents. 2, we're going to multiply 3 times. And on paper, we'd notate that with a little superscript, a little number up here, 2 multiplied by itself 3 times, which is repeated addition, right? 2 plus 2 plus 2 is 2, 4, 8. Oh, yeah, it comes back to 8, starting to get it up to a lot of dots there. So that's a whole number there represents how many times we're multiplying. What about repeated division? We can do that. We're not getting into the full thing, but if it comes out, we'll say if it's going to come out evenly, we'll represent that with a fraction. Because a fraction is like division, right? So like 4 to the 1/2. A fraction here represents kind of going the other way, which I'm going to jump ahead and just say that's another way to notate a square root. Hopefully you remember that. This symbol is what we normally use on paper. The square root is the opposite of squaring. Well, squaring is like a number times itself, right? 3 times 3, number times itself. We did it 2 times, so that would be 3 squared. So when we go the other way, in this case 4, what number times itself would give us 4? We know 2 times 2 would. But the important thing to notice is the exponent here is a fraction. 1/2. Just like the little 2 indicating we want the square root there, or cube root, or whatnot. Because oftentimes with programming, we have to notate it this way. Some of the common ones, square roots, might be built in, but a lot of times we'll just have to do a fractional exponent if we want to take a root. So that's kind of our core operations. So let me erase the board, and then we'll talk about the order, and then get into algebra, and then lead algebra from algebra into functions, and that's what we actually need for programming. So really quick rundown on all the review of the stuff we do in math. One of the big things that can be different is where you might remember a radical sign, the square root, a cube root, a fifth root, 27th root, whatever number goes there goes into the denominator of a fraction, because that's how we'll need to notate it in computers. Well, we're in Python, so two asterisks are going to be our exponent. It's like 2 asterisk squared. That means 2 squared, when the way we'd write it when we were first learning math, which gives us 4. I'll do a 4. 4 asterisk, so 4 raised to the power of 1/2, which we'll talk about that in a few minutes, how we put a fraction in there. Basically, parentheses 1 divided by 2. I guess I don't need to delay that till the more formal section. 4 raised to the 1/2 power is like the saying square root of 4. Square root's usually built in, but some of the higher ones aren't built in. So just remember, a fractional exponent gives us the same thing as a root. You can build it up the same way exponents build for multiplication. The fraction, well, the division, fraction does mean division. So that's saying repeated divisions. Repeated identical divisions. Let me erase the board and we'll get into the next section. The next thing here is kind of an order of importance, order of precedence. The order we do these operations in. So back in some math class or another, you were probably required to just memorize this. And something like that. I guess the traditional one is they have you memorize, please excuse my dear Aunt Sally. Your teacher may have created a joke out of it. The funny or inappropriate ones are actually better for memory, but obviously inappropriate is inappropriate for a classroom, so one way to memorize it. But in order that these the operations are carried out in. And I like to think of this as a staircase. Right? This little guy has a bunch of math to do. So first thing is parentheses, is the way we remember that. Really, that means any grouping. Any type of way we can group our number, because fractions group numbers, right? 2 plus 3 divided by 5 minus 7 times 2. This fraction bar groups our number. So things like that are important because when we type this in a computer, well, parentheses are the way we have to group it. So in a computer, we group those, then divide by 5 minus 7 times 2. And for a good rule of thumb, anytime you have this type of fraction, go ahead and put parentheses. Because if you don't need them, it'll just ignore them. Right? We don't want to do 2 plus 3 divided by 5 minus 7 times 2. I'll leave this up here for a second as we fill this up. The first thing we do is any type of grouping. Square roots or cube roots. Cube root of 27. Instead of 27, I'm going to make that like an operation. 25 plus 2. So still cube root of 27, but those need grouped into a single operator. That groups our numbers together. There's two ways to look at this one. This one would also fall in the second thing, which we remember that as exponents. Or that's the way we're introduced to it. It's actually our unitary operations. I'm just going to abbreviate operations. Our unitary ops. The operations that only take one number, kind of like the cube root thing here. I have it wrote out as this addition, but by the grouping rule, we would do that grouped part first, and we can only actually take the cube root of one number at a time. So that's a unitary operation. Squaring a number, 2 squared, or any number squared, if we're going to square it, all we need to know is which number are we squaring. It only takes in one number. So we do those first. Whichever way you're looking at it, built up from the counting like we're going through here, or that earlier thing about modern math. Any type of grouping, collective, any type of collecting things, then all our unitary operations. And we do all of the parentheses. We move up to the next step, do all of our unitary operations or exponents, move up to the next step, and then the MD, multiply and divide. Those get the same precedence. Or divide, and we just go left to right. We always do things left to right because sometimes it doesn't matter and sometimes it does. So if we just always do it in that order, we don't have to worry about thinking through whether it does matter or not. After we do all of those, we can move up to the next step. All of the adding and subtracting. That's, and again, it goes left to right. Sometimes it doesn't matter, sometimes it does, so we want to be careful if it does. If it doesn't matter, it's called commutative. That means we can commute the order of the numbers, right? Like commuting, we use that, talking about going to work, right? Driving to and from work. Switching the order. So kind of like how 2 times 3 gives us the same number as 3 times 2. The order doesn't matter there. But sometimes it does matter, so we want to be careful about that and just always do left to right. So we have that order that we perform all our operations in. And we can see from the order, if we neglected the grouping here in our numerator and denominator in our fraction, it would do the division in the wrong place. Because it's going to try to do this division before it does the addition or subtraction. And we want the whole quantity, 2 plus 3, divided by this whole quantity. Whereas this would give us 2 plus 3/5 minus the 7 times 2. But the grouping is very important. Watch that. So anything that groups the numbers, when you go to take it to a computer, put it in parentheses. And if you want to step out of that order in any place and define the order that you do want stuff to happen in, just throw some parentheses in there. And don't be afraid of throwing too many parentheses, because if you don't need them, it'll ignore them, and if you don't need them, they won't matter. If you do need them, they make a big difference. So that's the order we perform these things in. I guess the next thing is going to be getting into algebra, so I'll just erase the board and start over with algebra stuff there instead of trying to put it on half the board. So the next thing, I'm going to use this idea of keywords to lead into algebra. A lot of times, especially in programming, and all the math classes so far, with the review part, you probably remember the word problems. And we'd be given a statement and have to pull a math problem out of that statement. And usually we look for keywords to do that. And in programming especially, we're going to have to pull words from verbal descriptions to figure out the math that we need to do. Verbal descriptions. That lead to math equations. And there's a huge list of these keywords to look for. Just kind of the basic idea here. There's some that we'll start with equals. An obvious one is going to be is, was, are. The different ways we can say that. Becomes, leads to, different phrases and words that when we see those in a word problem, we know that's representing where our equal sign goes. Addition, we might see more than. Just anything that means increase, right? More than, increase, combines. Basically, any word that means some sort of increase. When we see those, that means we're going to add. Subtraction, kind of the opposite. We'll start with less than, decrease. Basically, any word that means decrease. Anything that's going to bring up decrease. And for all our operations, we have keywords like this to look for. The list could go on and on and on. English is a huge language, but hopefully the idea makes sense. Some sort of keyword that we can look for to put together a mathematical operation. And that's going to lead into some algebra stuff. Because often once we have an equation that will solve our problem, it's not going to be in the right form. So we need to do some sort of algebraic manipulation on it. So for example, just a quick example, let's say you have $5 to spend at the grocery. So have is kind of an is thing, right? So equals $5. A $5 bill in your wallet when you go grab lunch, right? And you're not very hungry, just feel like a couple pieces of fruit. You go in the grocery store and see the really nice apples or whatever you were thinking of are $1.50 a piece. How many can we buy? In that case, we'll put those words together and end up with some equation, right? $1.50, that's not going to come out evenly. Say the apples are $1.25 a piece. That way we at least get a whole number here. How many apples can we buy? Usually we just represent it with X. That's just a placeholder, right? Something to hold the place of this number so we can figure out what that number is. We draw a little picture of an apple. Little pictures take a long time to draw. And generally, we're used to writing the letters. They're quick and easy to draw, so, maybe something useful like A. That's how many apples, if they're $1.25 a piece, how many can we buy for a $5 bill, the $5 in our pocket, ignoring tax or anything. And with algebra, we always want to get back to a certain form. I'll use the A there. But ultimately, we want to have 1 times A divided by 1, either plus or minus a 0, equals some number. Because this is back to that very original part. We had the multiplicative identity, the thing that doesn't change anything. The additive identity doesn't change anything. The ones that don't change anything, we don't have to write. So if we ignore these multiply or divide by 1s and add 0, we just get A equals that number. So we always want to get it down to this form. And we just have to do whatever, we do the opposite operation of what we have. And this works because if we have an equation, we have a true statement. And anything we do to a true statement, as long as it balances out on both sides of our equal sign, will still be true. Right? 2 plus 2 equals 4 is a true statement. And if we took 3 times the true statement, just kind of distributed this 3 to every number in there, we get 6 plus 6 equals 12. So anything we do to a true statement, as long as it all balances out, is still going to be a true statement. So we always have to do the opposite operation. So right now, the way this is set up from that problem I made up with multiplying, so the opposite of multiplication, well, I erased the little order of operations, but the thing on the same step is the order is multiplication with division. So to cancel out multiplication, we divide by 125. Right? That's like a fraction with the numerator and denominator the same thing, so those are going to cancel out, which just leaves us 1 times a over 1, so that's where we get this part. But it has to balance. Like kids on a seesaw. That kid's playing on a seesaw. If another little kid comes running along and jumps on this side, this kid's going to go flying unless one of his friends comes and jumps on this side too. We just have to balance it out. We don't want one side of our equation to just go flying off to nowhere. We have to do the same thing to the other side. So we divide by 1.25. And here, all that canceled out, so we get the 1 over 1. We didn't have any addition to begin with, so we just have a equals something. And 5 divided by 125 is going to be 4.4. 4.25. 4 1/4. Wait, that's not right. I'll do it this way. 5 divided by 1 1/4 is 5 quarters. 5 divided by 5 quarters becomes 4. Yeah. I don't know where I was getting the extra part when I did that in my head. But 1.5 will go into 5 4 times. We won't punch that in calculators anymore. But that's the basic idea. We always do the opposite operation and try to get back to this whenever we have something algebraic. How much time was that? 8 minutes. Okay, so yeah, so I'll do another example. So like 2 times x plus 4 equals 10. Let's start away from our variable and work back to it. We undo any parentheses first, kind of multiply everything out, combine like terms. If we have more than one x, we can put those together because that's like saying how many x's do we have. And here we are adding, so the opposite of adding, subtracting. And we have to balance it out, so we have to do the same thing on the other side of the equal sign. This 2x equals 10 minus 4 would be 6. And now we are multiplying. The opposite of multiplying is dividing. So those would cancel out, and we have to balance it out. 6 divided by 2 would give us a 3. Just a second quick example on the basic concepts of algebra. Hopefully you've seen that somewhere, and we'll build it up. And I'm going to erase this board and then go over the key part of algebraic, why we want to be able to move things around for computer programming, why this is going to be important. And that's pretty much going to wrap up the video. Hopefully that quick review helps some if you haven't seen it in a while. So our algebra isn't reserved just for numbers like we saw there. This is a little bit more important for the computer part. I already erased it, but the letters that we use as placeholders, those represent numbers. So it's kind of like there's a number there, but we can do it all with those placeholders and not have any numbers in there. For example, the ideal gas law. That's a good starting point. If you had a chemistry class, it's usually capital P. You may have seen this. Pressure times volume is the molar mass times some constant times the temperature. That's how you were saying in chemistry class. I'm more familiar with physics, so in physics class, kind of the same thing. Pressure times the volume is going to be the number of molecules times the thing called Boltzmann Constant at a constant temperature. The same thing, just a different constant. Chemists use this one, physicists use this one. The capital N is the number of molecules, where N is the molar mass, a quantity that's actually we can work with, right? We can't work with one atom at a time. but that's for physicists. We think about one atom at a time. I'll just use this one. If we wanted, because this is kind of the wrong form for a computer to work with, right? We have two numbers over here. We're going to talk about functions in a moment. We need it in that form. We need to have just one number over here. It's a preview of what we're doing. So we can do those same algebraic steps. Maybe we want to know volume. If we know the air pressure, how many molecules of air are inside a balloon at room temperature, how big is this volume going to be? And just like we did on the algebra with numbers, the mix of numbers and placeholders, we always do the opposite operation. So here we're multiplying, so we would divide to get the v by itself, because those p's are just going to cancel out. And we have to balance it out. Do the same thing over here. And get volume is the number of molecules times that constant, multiplied by the temperature, divided by the pressure, and that tells us how much space a balloon would occupy for that quick example. But we're not restricted to numbers, and this one's going to be a little bit more important for programming because we have all placeholders. And again, mathematically writing it down, the one letter at a time is quick and easy to write. Typing we can usually do really quick, so when we're doing it in programming, we'd want to spell those things out, right? We'd actually spell out pressure times volume equals the number of molecules times Boltzmann's constant times the temperature. And then we do all the same manipulation. Because we want it to, well, if I wrote this out with all numbers, you can see that the process itself is independent of the symbols we use. Like 2 plus 3 times 5 equals 17. We do the same algebraic process with all numbers. Let's get back, I'm just going to pick a random one because there's not enough to solve for. Let's get back to the 3 by itself. So we start away from the 3, and multiplication is closer than addition whenever I say it that way. So the furthest away is going to be the 2. We're adding 2, so we have to do the opposite, which is subtract 2, which gets us down to a plus 0 here. And plus 0 is not going to change anything, so we don't have to write plus 0. This one we didn't do anything to, so that just copies down 3 times 5. And to balance out this minus 2, we need the minus 2 over here. We get 15. So now we wanted the 3 by itself, so we're multiplying. So to undo the operation we are doing, we have to do the opposite. The opposite of multiplication is divide by 5 in this case. 5 in the numerator, 5 in the denominator, those are going to cancel. Leave us with just a 3. And to balance out the division, we have to do the same thing over here. 15 divided by 5 equals 3. So the steps there are independent of what symbols we're using. And when we get to programming, that's the important part, the steps of how we do that. Because we need to get to functions. So I'm going to step back in case you need to pause for a second. I'm going to erase all this and get into the next part. But the steps are the important part, the algebraic steps of how we move things around. Because we need this concept called function. So the formal definition, if you saw it in math class, is a distinct output for any given input. A distinct output per given distinct input. If we have a distinct input, we need a distinct output. And whenever I'm helping people with math class and this comes up, I always refer to computers because most people are familiar with them. And I give this the definition. If it's not a function a computer will crash. So that's what I always say when helping people in math class with functions. If it would destroy your computer, it's not a function, which is a distinct output. Any input we give it is only going to have one output. You know, that's not to say 5 things aren't going to happen, right? We click on the spot on the screen, 5 different things happen, but that same 5 things happens every time, right? In the same order. That sequence would be the distinct output for that particular click of the mouse. Or another way to think of it, we don't want our users to be hopeful of what's going to happen when they click the mouse. When the user clicks the mouse, a very specific thing should happen. If we push the H key on the keyboard, a very specific thing should happen. So for any input we give it, there is a distinct output, clearly defined. That's function. Which means when we do it in math, we always want one single number equals whatever mess we have. So sometimes they'll get really, really, really messy on this side. As long as there's only one number. One number on that side. I'll put a couple arrows to express the importance of that. One number. One number. But we're probably talking about variables in math class, so one placeholder might relate more to computer programming. One thing on this side of the equal sign, and that's going to equal some sort of math operation. So that one I erased a moment ago. Pressure times volume. Oh yeah, I wrote both of them. The chemistry one. Pressure times volume equals nRT. Molar mass, number of moles times the constant chemists use times temperature. It's not a function because we don't have one single number on either side. If we wanted to know a certain pressure, well, we're multiplying, so we divide off the volume, and that gives us pressure as a function of all this stuff. So that's the important part of why we need the algebra. We need to be able to manipulate it into this one item equals some sort of mess of operations. Which that's not going to work for a computer, right? If we were programming that, well, we can't use juxtaposition for multiplication for one, so we'd have to write all those out. M times R times T. And this fraction bar means we're grouping things. So we need to make sure and group our numerator and group our denominator. And just for good form, go ahead and put parentheses. Anytime you have this, go ahead and put it, even if it's one number. It won't hurt. It doesn't take long to make two extra key presses, and it is worth the effort. It's a lot quicker to make 2 extra key presses than to dig through and find a mistake when you didn't make those 2 key presses. So even if it's one number, just form the habit of always grouping the stuff. It's a good habit to be in. And that's kind of why we need to be aware of the algebraic manipulation. Hopefully all that rung a bell very quickly, a quick review. Well, might as well, got a little bit of space here. More complicated math. We usually have a library. We usually have a library to do our complicated math operations. It'll look something like math dot whatever operation. For square root's a common one, SQRT, and then the number we want to take the square root of, which we find from a function or of some sorts. But as they get more complicated, and we usually have a math library to refer to stuff, which means you're going to check the documentation to see how to program those in. But this one, when you start with a verbal expression, you're going to jot down a formula based off keywords, right? Bunch of, so some number, make up a problem here. Do I have time? Yes. I'll say it out loud. Some number is twice as much as 3 less than the number. So some number, just call it X, is twice as much as 3 less than that number. Twice as much as 3 less than that number, so then take that number minus 3, double that, we get back to what the number is. That one's going to be a fraction in this case. It's not going to come out evenly. I just made up words off the top of my head there. But we're going to start with some verbal expression. Come up with a formula. We might not have it nice with one thing on this side. I could expand that. 1 more than a number. 1 more than a number is twice as much as 3 less than the number. You might notice this isn't quite going to work out. There's a fractional answer to it. It's going to be messy, but that kind of idea. We start with a verbal expression, turn that into a formula, do all our algebraic manipulation on it to get back to a function where we have one thing equals some mess of mathematics. Hopefully that quick review helped. If you need something in more detail, let me know. That is just kind of the covering basically all of math for those who haven't seen it in a while. If your math class was a while ago, you may not remember everything. So hopefully that quick overview stirred up some memories there. Let me know if you'd like this in a little more detail. We can meet up on Zoom or something and talk about it specifically, go through a bunch of examples. Hopefully that was helpful to stir up dusty old memories that you may not have used in a while. And the last little part here is going to relate directly more towards programming. We're going to be over here doing screencast in a moment. Just wanted to point out kind of the idea of what we're doing. I just went over to the bookshelf, grabbed a random introductory and intermediate algebra book. And so one of the best ways to practice is get one of these and open up to a section like this. Can't really read all those off the screen. There's kind of a glare. The sun's shining in the window behind the computer right now. But hopefully you can see that's the word problem section. Get your see if you can find an old math book, or another alternative would be to go to Google and look for, say, and search intermediate algebra review sheet. You know, kind of like a study guide before a test. There's a whole lot of those posted online. So you can find something like that to get practice problems and put those into a computer. So basically, we're going to go here in a moment and do a screencast of doing Python examples or doing some examples like this in Python. We're not going to go through the whole word problem. Well, maybe one word problem. I want to try to keep it under 10 minutes. This might have gotten kind of long, but I'm going to find a section here that has a couple of algebraic expressions, and we'll work through that on a screencast and putting that into a computer. And basically, to practice this, oftentimes you can go to Goodwill or any thrift store and find an old math book for $1, maybe less, and that gives you a whole bunch of practice problems. Or just Google review sheet from some particular class, and you'll likely find lots of study guides from somebody's algebra class that you can use to practice, and then use Python as a calculator to practice entering math in there. So let's go do a couple of examples of that to see how it goes, and hopefully this video helped. Obviously, it's very, very quick to cover so much, so it was mostly just trying to stir up some memories. One thing that I do want to make note of, because it will apply to us, multiply and add or. Some keywords. Some people hear that very young, like elementary school. I remember sitting in the 300 level math class and somebody was surprised because they've never heard that. Everybody hears it at different levels. General, multiply and add ors. That's kind of an important one in computers and when we get to set theory and stuff. But let's go do a couple examples out of this math book to show how to practice this. Demonstrate a quick demonstration of practice. And hopefully this video hasn't gotten too long and I'll get it posted for review purposes very soon. Okay, so getting some practice of particularly how to apply this towards programming. As I was going through getting my degrees, basically in every class I took, I would write programs just to get lots and lots and lots of practice. So just kind of pointing you in that direction here. So the idea is as you go through your math class, as time allows, because obviously time's a precious commodity for most of us, but as time allows, try to write programs to solve the problems you encounter in, well, maybe not just math class, all your classes, just to get lots of practice at programming in general. So to get you started here, I'm just going to open the Python interpreter. We'll do it right in an interactive session. So I have a couple problems here to practice. I just opened to a random section that has some equations. So for example, number 6 on this one, in this book that I opened, gives the problem 5y minus 2 equals 53. So still putting comments in here. But kind of like we saw on the board, we want to do the opposite operation. So we start away from the variable, which is going to be that subtract 2. We have to do the opposite operation to cancel that out. So we were subtracting 2, so we'll add 2 over here and add 2 over here as well. Plus 2. That looks like an equals line. Which leaves us, well, that 5y, nothing's changed with it. Minus 2 plus 2, that gets us back to plus 0, which doesn't change anything, so we don't have to write that part. Equals 53 minus 2, or 53 plus 2 would give us 55. And then once again, we want to do the opposite operation. So right now, 5y means we're multiplying 5 times y. So the opposite of that is going to be divide by 5, which will cancel all that out. And we have to balance it out over on the other side of the equal sign. So divide this side by 5. And that gets us down to that function form I was talking about. Don't want a 3 there. That gets us down to that function form I was talking about, because now that 5 divided by 5 is going to cancel out, and we're left with just a y. And over here, 55 divided by 5 equals 11. Kind of how we solve it. But to write this out, I'm actually going to write those steps. So we have y equals, well, the first thing we did is add 2. Well, we started with plus 53, so y is equal to 53, and to that we added 2 plus 2, and then we divided by 5. Again, order of operations is important. We don't want to take 53 plus 2/5. We want to make sure and put parentheses in here. It's like 53 plus 2, and then that number divided by 5. Then y equals 11. So hopefully that makes sense of, most of this would probably be done on paper. That seems like it'd take a lot of video editing to go back and forth. But that's just a random problem I found in this book, or you can Google for review sheets or see if you can find some sort of example problems to use And basically just practice using Python as your calculator to punch that in. But do you see how those steps, those algebraic steps, led to this? Just put them all in at once. So another one, let's try a word problem example. Okay, so I've just kind of opened the book here to a random word problem section, which I guess I'll read off here instead of trying to type the whole thing in. Hopefully everything comes through the mic clear. But just picking a random problem here out of this book. It says, the manatee, Florida's state mammal, is an endangered species. An aerial wintertime manatee census counted 2,817 of these animals in 2007. This was 296 fewer than the number counted in 2006. What was Florida's manatee population in 2006? So the basic idea here to practice this is use Python as your calculator. So what was the population in 06? So population 06, I'll put 2006, 2006, population 2006, population in 2006. There we go. My keyboard was sitting on the mouse pad and it kept jerking around. I didn't even look down to see why it was doing that. Okay, population in 2006, well, they told us in 2007 there were 2,817 of them, and this was 296 fewer than, 2007 had 2,817, and it was 296 fewer than 2006. So we know 2,817 is a little smaller than the population in 2006. So to get back to that, from the 2007 population to the 2006 population, we need to add that number. Right? Because as they gave the problem, that's kind of saying population 2006 minus 296 equals 2,817. But we have two things on the wrong side of the equal sign. So we need this minus 296 to be brought over here. So algebraically, like we did up here, we'd add 296. I'll take that out of there. Equals 2,817 plus 296. And that should give us the population 2006. It's 3,113. But that's the basic idea there. Just open up the Python interpreter and use it as a calculator. And find an old math book or just do some Google searches for practice problems and practice. Because it does take a lot of practice to get used to it. Hopefully this quick crash course helped and kind of point you in the right direction. You'll just want to, from here, just find random math problems and practice them and use this as a calculator. So hopefully that helped stir up memories about mathematics for those who haven't seen it, haven't had a math class in a while. And then this is what you'll want to do to get used to going from the math book to, I keep saying math book because math books usually have answers to odd numbered questions, so you can check and make sure you're doing it right, part of the debugging process. But get you some math practice problems and just practice, use those as programming practice problems. Hopefully that helps some. Let me know if you need a little more review or some more tips or something on where to go. We can meet up in a Zoom session and go over stuff.